So mathematics of complex and intelligent systems. So basically we want to kind of try to address two fundamental questions. So here, what is complexity? What is complexity? So, and what is intelligence? So these are actually two very difficult questions, right? So what is complexity? So first of all, let me say very much in advance that there is no unique answer to this question. So complexity is a notion that appears everywhere in science, also in the common language. You know, when you talk about something that is very complex, and but there is no unique definition. So in different areas in different disciplines, the notion of complexity is very much used. It's used in mathematics, in physics, in biology, in economics, in social sciences. And in the definition or the notion of complexity, it's adapted to the specific kind of subject or area of application, and to serve the purpose of understanding something about a system that has some specific features. So one of the features that is very common when we talk about complex systems is the fact that when we think about a complex system, we think of something made of very many components that interact with each other mutually, no? in somehow a complex way. Also, when we think about complex system, we think about something that is whose behavior is not easily predictable. So we might have a very clear snapshot of what is the configuration, the structure of this complex system at a specific time, but it might be very difficult to predict how it evolves. Also, its evolution might be subject to random effects, okay? Random factors that we don't control, and this means that the system will be truly unpredictable, and you need to develop some statistical ideas, hopefully, to understand what's going on over there, right? So definitely the concept of complexity is very complex, right? So, still it's very important, okay, because most of the things we are interested in, so the real world, biological organisms, what is life, all these aspects, go down to the notion to understanding what complexity is and how we actually relate ourselves to complex systems, how we understand them, how we control them, how we can reproduce them, okay? So, and how is this related to the notion of intelligence? So what is intelligence? So intelligence is also something quite difficult to define, because there are many different forms of intelligence, right? So when we think about an intelligent system, we think about a system that somehow is able to do something by itself, right? So make a decision, or solve a problem, or most simply follow some set of instructions. Okay, so this is a form of intelligence. It might be not very evolved depending on the set of instructions. It might not be a very evolved type of intelligence, but it's intelligence. So, an intelligent system is a system that is creative. Just things about living organisms, human beings, that can be creative, right? In creating new solutions, or creating art, creating something that did not existed before, right? So, and why is the notion of intelligence connected to the notion of complexity in a way? So basically, because intelligence always emerges when complexity is the background of it. So intelligence emerges as is a sort of emergent feature, okay, of complex systems. So at some point, when you have a complex system interacting in a complex way, doing very complex things, at some point collectively you see that this system develops some sort of intelligence. For example, a system can have a memory of the past, as living organisms often do. Living organisms often do have a memory of past. So if there is a memory, there is the ability to learn, and then once a system can learn, can make decisions, and then possibly build something using the knowledge that is somehow stored in this system. So somehow today, kind of, we think of intelligence as an emerging feature of complexity. Although the history of complexity and intelligence is a history as old as the world, you know. So if you think that first living organisms appeared at least 3.5 billion of years ago, so it's a very long story, right? On the other hand, now when humans started, you know, thinking about these things, of course, the natural question is, you know, how do we understand this? And once we understand this, is there a way to reproduce this artificially, right? And this is the story of the history of the artificial intelligence. So the idea to build something, say a machine, able to behave as an intelligent system, store memory, make decisions, solve problems, do something, learn, do something independently. Although all these aspects are very complicated, you know, and there is a separate, you know, a story for each of these. So humans started thinking about, you know, how to build a machine or delegate some tasks to a machine. So very early in the history, you know, in the Hellenic Greece, astronomers built like a device called the Antikythera, and it was like a device to predict decades in advance the position of planets, which is a form of, you know, it's a form of calculator, so very rudimentary, but a calculator that can actually make, to which you can delegate a complex set of tasks as calculating the position of planets. So more recent, so in the 19th century, Charles Babbage, so it's kind of the inventor of the idea of a computer, invented the so-called difference engine, which was a mechanical calculator, like a mechanical calculator made of rotating parts, which could calculate polynomial approximations of functions, which is a quite complex. I mean, the average person is not able normally to calculate polynomial approximations of functions. So, but the revolution starts actually in the 20th century, okay, in relation to the idea of building a machine, creating something that can actually, you know, perform complicated tasks and possibly produce new knowledge. So this story starts in 1936 with Alan Turing. Okay, Alan Turing, so I'm sure you all know something about Alan Turing. So he published this very fundamental paper on computable numbers, where he basically developed the idea, okay, of a computer. So theoretically, so he developed the idea of a machine which can perform independently calculations like compute numbers. So, for example, pi to any number of digits. And then, you know, identify when this task is complete and end. Okay, so this was the very first revolutionary piece of work, okay, which opened the idea of the modern computers. Computers that we got here in this in this classroom, on your mobile phones at home, and so on. So the second kind of important step happens in 1945, okay, so, and when, around the circumstances of the Second World War, when the so-called von Neumann architecture was introduced. So the idea of the von Neumann architecture is basically is about the structure of computers that modern computers still have. You probably have heard about random access memory, RAM memory, right? And this is what von Neumann and his collaborators devised. So they basically devised the practical way computers work. So the way the computers store information, okay, in their memory. So imagine something like a two-dimensional array made of magnets, okay, so very small magnets, and each of these can carry one bit of information. Okay, so the type of information the computer can process is a very simple type of information. It's a bit of information, so it can have two possible values. Conventionally, either 0 or 1. Okay, but in this matrix, you can store any sequence of 0 and 1s. You can erase it, print a new one, and in this way, change the values in this matrix and you can start from an input, follow the ideas of the Turing machine, and come with an output. Okay? So clearly, the language the computers understand, based on the so-called von Neumann architecture, is the binary language, and basically all the operations you can perform using a computer, fundamentally, they go down to arithmetics. Okay? Arithmetics is the mathematics of computers, essentially. So everything goes down to that. And this binary language seems like a limitation, but actually allows to perform many things. Okay? So first of all, we know that any number, okay, any integer can be, and any number can be transformed, okay, up to a certain approximation, can be transformed into a binary number. Okay, we can always write the binary equivalent of any number expressed in decimal base, right? And also, so for example, if I say the number 2, okay, this is in binary language is 1 0. Okay? So if I say the number 3 in binary language, this is 1 1. Okay, so if I add them together, okay, so this is 5, okay, and this is 1 plus 0 is 1, 1 plus 1 is 0, and I can is 1 0 1. Okay, so and this is a simple way. This is a simple way I can do an operation, the addition using the binary language. So it works exactly in the same ways as in the decimal case. Okay. The only difference is that this can be implemented into a computer. Okay. Also, the computers can follow a sequence of instructions. So you can store numbers, you can elaborate numbers, and you can perform logical operations. Okay. But logical operations are also based on the binary structure, right? Because if I say that P is a proposition, okay, let's say this proposition is square 2 is rational, okay, so this proposition can be true or false, right? So there are propositions to which I can assign a truth value, right? And in this case, of course, the proposition is false. So then I can take another proposition, say this proposition, say 4 is even, okay, and also I can assign a truth value to this, okay, and in this case this is true. So when I can implement logical operations into a computer, and I can elaborate truth values because they are intrinsically binary. So I will say, for example, that true is 0 and false is 1. And then when I consider a combination of propositions, say P and Q, okay, this is the connector, the logical connector, and I know what is the truth value of P and the truth value of Q. I can ask myself what is the truth value of this the combined proposition P and Q. And when I come to this, I need to implement into the computer, okay, what is called a truth table. So I can put P here, Q here, so P can be true or false, 0, 1. Q can be true or false, 0, 1. And the truth table for P and Q says that the combined proposition is true only if both are true. It is false in all of the cases. So if both are true, 0 and 0, it will be 0, and it will be 1 in all of the cases. I can take the proposition, say P or Q, okay, P or Q, and the truth table will be like this: P, Q, 0, 1, 0, 1. So in case of the connector OR, the combined proposition will be true if at least one of the two is true. So if I have a 0 here, it will be true. If I have a 0 here, it will be true. It will be false only in this case. I can also compare two propositions, say P equal to Q, and compose the truth value for this type of operation. So everything is based on, as you see, on two digits. So if they are equal, okay, so it is true only if they are equal. So it will be 0 on the diagonal and 1 on the anti-diagonal. Okay, so truth table is a simple way to take into account of all possible cases, okay, and it shows that I can implement, I can combine many propositions, sequences of complex propositions, and tell a computer to elaborate them and come up with the final truth value. So basically I can ask a computer to use the logic to prove theorems, okay, and gain new knowledge. One final thing before we move on to more kind of modern things. So just if you look at this, what is the connection between these two? So if I think about the addition, I just did. You see, when I perform the addition, I have two numbers, right? So P and let me call these two numbers small p and small q, right? And these two numbers can have like digits 0 or 1, right? And basically, if I do 0 plus 0, okay, this will be 0. 0 plus 1 will be 1. 1 plus 0 will be 1. And 1 plus 1 will be 0, and I carry 1. So I have this, in order to do the addition, I need this truth table, but it's not enough because I also need the carry operation. So what is the carry operation? The carry operation is simple because you see that I carry only if both are equal to 1. Otherwise, I don't carry. So it would be 0, 0, 0, and 1. Okay. So you see there is a connection with what I wrote here and what I wrote here. So the addition, okay, the addition here looks very much like the equality. It coincides with the equality, right? And the carry operation coincides with the OR operation. Okay? So basically the addition can be reduced to two fundamental logical connectors. Okay? So, and this is how basically the computer works. Computers have got like very dense circuits which can elaborate, you know, binary operations of this form. But if you bring them down to the elementary operations they do, everything reduces to this type of logic and arithmetics. Okay? So the advantage of modern computers is that these integrated circuits contain, you know, billions and billions of units of this type, and this allows to perform extremely complex operations. Okay? So now we can just move to the second part of this talk. Although modern computers can do very many calculations very, very fast, okay, there are things that still modern computers struggle to do. Okay, I'll give you an example. And so imagine, okay, I drew a picture of this type. So what do you see on the left? I would say a handwritten number 1, right? And what do you see on the right?
Could be 1, could be a 7, could be...
Yeah. So it's most likely a handwritten number 1. It might be a 7, but most likely is a number 1. So this is 1. Okay. So now let's take this for example. Okay, what do you see on the left and what do you see on the right?
Cat.
Possibly in both cases, right? My drawing is a bit surreal, I would say, but so most likely in both cases, on the left and on the right, we see a cat.
Looks a bit like a fox.
Huh?
The right looks a bit like a fox.
More like a fox. There is a chance it might be a fox, or maybe some of the relatives might be a fox. So it's so most likely this is a cat, but there are some other options to which we might attribute less smaller likelihood. Okay? So anyway, so we came to this conclusion quite quickly, right? The thing is that now try to think about how to program a computer, okay, to tell the difference between this and this, this and this, and come possibly with some probability to the same conclusion. So how do I tell a computer that this is a number one? This is also number one. And how do I tell the computer when this picture ceases to be a number one? Maybe put in a context, or if I just change it slightly, okay, like that, to look more like a number 7, for example. So if you think about if you think about a cat, the task becomes even more complicated. Also, because some of us see a fox, some others see a cat, some others might see a friend. So there might be many options, right? Although a cat can be a friend, so that's no contradiction. Logically, it's fine. Imagine now how to instruct a computer, okay, to get this input and come to a conclusion. So when we use our computers, stored programmed computers, so based on the Turing machine, von Neumann architecture, we need to provide the computer with very detailed and precise instructions. When we write a program, we need to provide precise instructions and also predict all possible scenarios to make sure, okay, that the computer at some point will close the loop, right? So, because you don't want to create a scenario where you put an input and the computer runs forever without providing any output, right? So you need to predict all these scenarios, and we see how complex this is. In this case, the idea of providing specific definition of what is the picture of a cat, okay, and make sure that the computer, the program can recognize, can come to the right conclusion is very challenging indeed. So this suggests somehow that a change of paradigm, okay? So, and what I would want to go through today is, even by considering a specific example, show you by an example how this paradigm needs to be changed. Okay? So we said that in the computers are based on logic and arithmetics. Okay? In order to overcome this problem, we need to invoke something different, something relatively more modern, 17th century. And this is Newton's second law. Okay? So, what does Newton's second law say? So, even Mickey Mouse knows. Okay, ma equal to f. What does it mean? So, I take a particle of mass m. The resultant of the forces is f. Okay, and then we know that acceleration can be written as the second derivative of the position. So the second derivative of the position, the vector position x is a function of t, and if you basically solve this equation and you have an initial condition, you can extract the position at any time for the particle. So there are different, this equation might be very complicated, very hard to solve, depending on the form of the force F. And an example of a force F, okay, if you want to give an example, so let's take a fixed point on a line, and let's consider a mass m, okay, constrained on this line, and suppose that this mass is subject to a central force. A central force points always to the center, O, okay, and this force I can. So since it's a one-dimensional problem, I can remove the vector sign. So F is just a component of the force. So the force is defined, in this example, as minus k times x, where k is a positive constant. Okay, this is called the Hooke's law. It's a simple example of a force which changes linearly in space. Okay, what's relevant about this force? Many things, but one of these is that this force can be written as minus the derivative with respect to x of u, okay, where u is 1 over 2k x squared. U is called energy potential, right? So the special thing about this force is that u is the energy, the force can be written as the gradient, okay, of a function of one variable, u, function of the variable x, called energy potential. So what does the energy potential tell us? So basically, if I want to draw, in this case, the energy potential, so this is a parabola, right? And the profile of the energy potential is something like that. Okay? So there is this minimum here corresponds to the origin, the center of the force, and it's the point where the system is at rest. Okay, so, and it's a fixed point. So if the particle starts here, it will stay here. It's not subject to any force, because here the gradient is 0 and the force is 0. So if I displace the particle from this equilibrium position, okay, so I put it here, the particle basically will tend to fall towards the center, the minimum of the energy potential, and will oscillate around this point. So whenever I take, what is the philosophy of this? Whenever I take a point, I put the mass somewhere in space, subject to this force, it will tend to accommodate itself around the minimum. So the minimum of the energy potential is an attractor. So it basically tends to keep the particle orbitating around this point. Okay? So this energy potential is not the only type of potential you can consider. We can consider also more complex potentials. Okay, I'm not writing the maths here. I can just I just draw a picture. So we can have like an energy potential U. Okay, so you can imagine something made like that. Okay, with many minima. Each of these minimum is a point of stable equilibrium for the particle. So if I put the particle somewhere in the vicinity of the minimum, so the system will recognize where is the closest relative minimum, okay, and it will tend to accommodate itself around that minimum. Okay, so naturally, this dynamical system naturally will accommodate itself around the point of lowest energy. Okay, and this is dynamics. So this has to do with what I said happens for one particle, but that actually happens if you consider a system, a complex system made of many particles interacting with each other. In this case, the system of many particles, if you have an energy potential, will tend to accommodate itself around the point, the closest point of relative minimum. If I add, well, these points of minimum are important because they are stable in all senses. If I add a little random perturbation, still the particle will tend to will see this point as an attractor. So it will tend to gravitate to orbitate around this point. Okay? So in each of these, depending on where I start, my particle will accommodate itself around the closest point of minimum. Okay? And this is true for one particle, it's true for many particles. Okay? So now you might ask, and I will understand your surprise, what has this to do with artificial intelligence at all? Okay? And this is the question I want to answer. And let's consider the following problem. I was told here I drew some pictures, right? So now I want to take an example of a picture, but a simple picture, right? So this picture is a black and white picture, okay? So made of 4 pixels, okay? And imagine that my picture is this one, okay? It doesn't look like anything specific, but it's a picture. It's a distribution of black pixels and white pixels, okay? And then I want to build a device able, okay, to take this picture as an input, okay? So then what is my model about? I think about the brain, how the brain is made. The brain is made of neurons and connections between neurons. So the brain I consider here is a brain made of 4 neurons. And these neurons are connected. And I assume, okay, that all these neurons connected, what does it mean connected? They interact in some way. There is a force between them. So something like that. And the strength of the force is given by a parameter, and I call this parameter beta. And I assume that for simplicity, okay, for the sake of simplicity, that the strength of the force is the same for all pairs. Okay? So I need a little bit of notation. Okay? I won't go much beyond the notation, but I need the notation. So I say that the white pixels are 0, okay, and the black pixels are 1. So then this picture will be a matrix, something like 0, 1, 1, 0. Okay? And since I want to think about something that I can give to a computer as an input, I represent this 2-dimensional array as a 1-dimensional array, as a vector, where basically I put in sequence all the rows. Okay? So this will be 0, 1, first row, 1, 0. Okay? And this I call x. Okay? So this picture is basically equal to this vector. Okay? Sequence of zeros and 1. So my neurons, okay, are very simple neurons. Okay? They are not very clever. So they can have only 2 possible states as well. This type of neuron is called perceptron. They can either fire a pulse or an electric pulse or not. Okay? So, and then I can say that one state is called -1, okay? And the other state is called +1. So, and then by convention I build this in such a way the white pixel corresponds to -1 and the black pixels corresponds to +1, okay? So, this array will be y, and this can be written as 2x minus 1. So, if I take the component, if x is 0, y is -1, if x is 1, y is equal to 1. Okay? It's just a map between this picture and these pixels, and this little network. Okay? A network made of neurons all interacting in pairs. Okay? So the state of each neuron, so the state of a neuron, I'll call it, so let's say this is the component of, or let me just make, I say that the state of the neuron, I'll call it the ith neuron, okay? I'll call it SI. Let me use this notation for, which is basically the ith component of the vector y. Okay? I call SI the state of the neuron. It can be either -1 or +1. Now I have the system interacts. It's like a dynamical system, and I can define an energy potential for this. This energy potential, I define it like this. Minus u, I put a minus on this side just for convenience, is beta times the sum for all I different from j of Si times Sj. So basically this potential is basically the sum of all possible interactions multiplied by the strength of this interaction. Okay, this is the energy potential for this system. And once I have this system globally, I want to explore one of the things I can do. I can do many things. One of the things I can do is to explore the global behavior of this. I can see, imagine, I'm taking this as a simple example, but imagine you have very many of these, and deciding whether there is one, if you compare two configurations, deciding whether there is one extra black pixel in one compared to the other might not be relevant. The picture of one, okay, or the picture of the cat, if I change only one pixel, will not be important. What will be important will be some sort of global information. I need to look at global quantities. The simplest global quantity you can see, you can consider and calculate is, for example, the total number of, the average number of pixels. Okay, so it will be 0 if half is white, half is black. It will be 1 if there is a majority or larger than 0 if there is a majority of black, smaller than 0 if there is a majority of white. So what makes sense to calculate is the average, okay, of the neuronal state, okay? So which will be 1 divided by n. In this case, n is the number of neurons, is equal to 4, okay, times the sum of all possible SI, okay? So now we will remember what we said about Newton's law. Okay, so this is an aspect of the model, right? So S bar, I can calculate, for example, the average. There are other quantities more detailed that I can calculate, but let's focus on this as an example. So another element that is concerned with complexity, as I said at the beginning, is randomness. There is always some kind of randomness, some random perturbations that might change the state, flip the state of the neuron. For example, the neuron just does not respond to the initial stimulus, or for whatever reason. And what I want to do is also to model this randomness. So I need to think about a probability, okay, define a model which takes into account of the fluctuations, okay, that depend on a random factor, okay. So an example that is it turns out to be very useful in the applications is a probability defined like this. The exponential is called Gibbs distribution, okay, and it's the probability is given by the exponential of minus u divided by, let me write it and I'll explain what it is, the sum of the exponential of minus u, okay. So the sum over what? Over all possible configurations of pixels or configurations of neurons, okay? Over all possible, basically, pictures I can feed into this little brain. So you see that u, the value of u depends on the specific sequence of 0 and 1s. So it depends on the specific configuration here. So for each configuration I can calculate a specific value of u. And then this probability will be the ratio between the exponential, okay, of minus u divided by the sum of this exponential for all possible configurations. And this is the probability to find the system in a specific configuration. So you see that the smaller is u, okay, the smaller is u, the higher is the probability. Okay? Because I've got a minus u here. So this probability, okay, is consistent with the idea that the system tends to accommodate itself around the configuration of minimal energy. Okay? So let's take a look at a simple example. Okay, so this particular example. Let's look at all possible configurations, right? So I can have a configuration that is totally empty. So a picture, the empty picture, white picture, okay, the blank canvas, right? So then I have, how many ways do I have to make a blank canvas? Only one, right? So I don't know. If I rotate it, it doesn't change, right? So then I can have a configuration with one black pixel only, so this one. So how many ways do I have to make a configuration of one black pixel? I've got 4, right? So I rotate it every time. I rotate it 4 times and then I go back to the original. I get 4 different configurations of one pixel. So then I have a configuration. I can have a configuration with 2 pixels like this, and I have 4 of them. Again, I rotate it and I get 4. Then I can have another configuration of 2 pixels made like this, and I have 2 different of them. So I flip black and white and I get a different one. I flip again and I go to the original one. So then I can have a configuration of 3 black pixels, which is the same, complementary to the configuration of 1 black pixel. So, and these are 4. And then I have a configuration of full all black pixels. And there is only one way to do it. So you see here, I've got the configuration of 2 pixels. I have 6 ways to make configurations of 2 pixels. And but let's look at the energy. Okay, so what is the energy? Is the sum, okay, of all possible products. We see that the highest value of this, or if you want U minimum, okay, corresponds to the configuration, to the empty configuration of the full configuration. Because I have the product Si times Sj, okay? So then if they are all 1 or all minus 1, I will get the same result. This 2 corresponds to the, from the point of view of this probability, the configurations that are more likely to happen. On the other hand, there are less ways to produce this and these configurations. There are more ways to produce configuration of 2 pixels. So this is more favorable from the combinatoric point of view. So configurations of 2 pixels, so the average S for the configurations of 2 pixels is 0. The average, the arithmetic mean for configurations of blank pixels is minus 1, and the arithmetic mean for the configuration of 4 full pixels is black pixels is 1. So it is not obvious a priori, so to decide if I randomly pick a configuration of pixels or a configuration of neuronal states, okay, if I will see more likely an empty or full, which is basically the same information, or a picture with equal number of black and white pixels. It's not obvious a priori because there are 2 different factors. This is favorable. These two are favorable from preferred from one point of view. These two are preferred from another point of view. And the key point here is actually, so the key element here is exactly this interaction, this constant of interaction. So before, how do I deal, okay, with this experiment? So I pick a random configuration, okay, of neurons, and so I start from a random configuration of neurons, and I want to find the configuration where this system of neurons accommodates itself most likely, okay? How do I work this out? Basically, what I have to do is to calculate statistically the expected value of S bar, okay, based on this probability. What is the expected value of S bar? The expected value with respect to this probability P is just the sum over all possible configuration of P times S bar. I emphasize here that each P here depends on the configuration as well as each S bar. And then I ask myself, okay, what is the expected value, S bar? I won't go through the mathematical details because it will take some time to go through the way you calculate these things, but I'll give you the result and make a comment. So for this model here, it's possible and not very difficult to calculate this number here, expectation value of this average. It's given by this formula here. So the expectation value of S calculated with respect to this probability, okay, is the hyperbolic tangent of beta times the expectation value. So it's an implicit equation. So in order to find S, this expectation value, I need to find the zeros of this equation here. Just to give you an idea of what to expect, I can expand in Taylor series around 0 this hyperbolic tangent, and this gives me, so beta S bar minus 1 over 3 beta cubed S bar cubed. Okay, so this is an approximation, Maclaurin formula to the third order. So this tells you that S is the solution of a cubic equation. So there might be one solution, there might be two solutions, there might be three solutions, up to three solutions. Now, what the number of solution depends on what? It depends on beta. If I draw the solutions, I put beta on the horizontal axis and I put the value S bar on the vertical axis, so you will see that the solution will be 0 up to the point beta equal to 1, and then there will be three solutions, okay, three solutions, so two symmetric solutions like this, and one solution is still 0. So 0 is always a solution, okay, but then I have two additional solutions here. So if I look at the energy potential, so actually the expected value of the energy potential, so if you look like this. So there will be two stable points and one unstable point of equilibrium. So S equal to 0 is a stable point, and these two values here, okay, that depends, so they will tend to 1 when beta increases, 1 and minus 1. So this corresponds to, these are two minima, okay, two stable configurations. So for beta large enough, this S bar will be close to 1, minus 1, and this will be close to plus 1 for beta large enough. Okay, so beta much larger than 1. Okay, so basically there are two. This little brain is not very clever. So if I start from any configuration, okay, any configuration of pixels, so the output will always be the same, depending on the strength of the interaction. So basically, if beta is small, there is only one solution, so the output will be a configuration of two pixels, independently on the input. If beta is large, there will be an output more complex, where there is a majority of either black pixels or white pixels, but these are symmetric. Okay? So this brain is not very clever, but actually provides a mechanism, okay, to start from a configuration and select from a configuration and select a specific configuration, okay, which is the equilibrium configurations. And the way I reach this configuration is based on this, the principle of minimization of the energy, okay, so that I stated in relation to Newton's second law. Okay. But how we go to the next step? Although this machine is not very clever, there is a way to change, to adapt, modify, and upgrade this machine to make it do more kind of interesting things. Okay, so the idea, okay, to improve this this machine, okay, was introduced. was introduced in 1982, okay, by John Hopfield. Okay, and this is what we call the Hopfield machine. So what is the idea of Hopfield? So Hopfield say, okay, so I've got a beta, so the picture is the same. I've got a picture here, and then I map it into a set of neurons, all linked together. But Hopfield says, okay, imagine, okay, so I want beta, it's not enough to ask to have beta as a scalar number, just as a number. So beta is a matrix. Beta 1t and so on. Beta is a matrix. This means that each pair of neurons can interact differently. Okay, so each pair of neurons has a specific type of interaction. So if this will be beta 1, 2. If I say this is 1, 2, 3, 4, this will be beta 2, 4, and so on. Okay. First of all, we make beta a matrix. Second thing, okay, that Hopfield suggests is the following. Hopfield says, imagine that we want to use this machine, we want to memorize a certain number of patterns. What does it mean, memorize? It means that I have my energy potential, okay, and each of these minima, okay, corresponds to a specific configuration of black and white and black and white pixels, right? And I want to construct to choose beta in such a way this minima corresponds to given configurations, given pictures. So I have a picture, I call it x1, okay, and this will be a sequence of 0 and 1. I have a picture, I call it x2, and this will be again another sequence, x3, and so on, okay, as many as I want, okay. These patterns, okay, I want to construct the network in such a way these patterns correspond to the minima of this of the energy potential, okay. And in Hoffield's recipe, okay, is to provide the way to find the right beta, the matrix that realizes this scenario. So this minimum corresponds to x1, this minimum corresponds to x2, and so on. Why do we want to do this? We want to do this because if we start from here, from a configuration here, that is not quite a pattern, it's not at all a pattern, so the system will relax itself around the closest minimum, the pattern that is more resemblant of the original input. So you start from a configuration, and the system will relax, will provide you an output, okay, corresponding to the pattern that is somehow statistically, okay, and dynamically closer to the original one. Okay, and Hopfield recipes is the following. So beta is equal to the sum, okay, so if I have the x are the patterns, okay, and then if I have x, I can construct, for x1, I can construct y1. It's just a simple transformation. So if I have x2, I can construct y2, and so on. So beta, by definition, according to Hopfield, is the sum over all, say, k from 1 to, say, there are m patterns, so say that I want to memorize a number m of pictures, so of what? So beta ej, each component will be yki, ykj. I basically combine, I use the patterns, okay, combined in a suitable way, I multiply corresponding for each k the pair yj, okay, and then I construct the matrix, this matrix beta. This matrix beta is such that if I look at the energy potential, so the minima will correspond to these patterns. There are some subtleties I'm not going into, okay, but this is the kind of the core of the concept. So, and then Hopfield suggests an algorithm to start from an initial condition here, an initial configuration, and then converge to the closest minimum, to the closest pattern. Okay? So this the idea of the algorithm is actually simple. So you take a neuron, okay? So you take a neuron, this neuron will be connected to a number of other neurons. So each of these has a strength beta EJ. Okay, so, and then I'll basically weight, okay? I'll consider the contribution of all the neurons interacting with my neuron. This is I, so I consider all the contributions, all the states weighted by the specific strength of interaction. So if pushing up +1 prevails, this neuron will be +1. If pushing down -1 prevails, this neuron will be -1. Okay? I do this for each of these neurons, and then I will converge so to the closest pattern. Okay? So to show how this works, so I did a little simulation in the computer. So to show you how this actually materializes when you want to see the machine at work. All right. So now I take a picture 15 by 15. I can do some better, no, but it will take longer to calculate. I take a small brain, 15 by 15 neurons, okay? And and then I first want to memorize, I decide what the patterns are, okay? I want to memorize the pattern. So I choose just 3. So this pattern is 1, okay, the number 1, okay? Big pixel, but it's number 1. So this pattern is the number 7, okay? And this pattern is the number pi. I build now my beta, the matrix beta, using these 3 patterns, using the rule I just explained. And what I do, okay, I build beta in this way. What I do now, I want to provide an input, a pattern, a random pattern. So what do? I choose, let me choose one of the patterns. So say I choose the number 7, okay, I start from the number 7. I flip randomly, okay, some of the pixels to perturb the number 7. Imagine that I'm in the dark, the view is partially obstructed, okay, and I can't really see all details of the picture. So some random pixels are altered, okay? So, for example, okay, I can say flip 1 in 20 pixels. In this case, it will be pretty much the 7 plus some perturbation. And I can say this is a 7. Now, I put this into the as an input in Hopfield algorithm, in Hopfield brain, okay? And then I let it calculate, and it says, yes, this is the number 7. This connects to this pattern in my memory. I know what it is. This is a number 7. But I can try to do something a bit more challenging for him. So I can say, let's flip 1 in 20. I flip 1 in 20 randomly, okay, and then I see, okay, now it's already more difficult to decide what this picture is. I've got in my memory many things. In my memory I've got 1, 7, and pi. I have to decide which one it is. So I give it as an input to Hopfield's brain, and Hopfield says, this is a 7. And I can do, of course I can play around with this. I can flip, say, 1 in 5, okay? And this is what I get. And then I have to guess what it is, okay? And Hopfield still tells me that this is a 7. And let's try to flip. So actually 0 is included, so I say 1 in 3. This is why it's quite hard to recognize anything here, right? So I put this as an input in Hopfield algorithm, and it still says that it is 7. So because the algorithm kind of is able to capture correlations between pixels that visually we don't capture. Okay, so then we can play around with this algorithm. Of course, we can make it more fancier. You know, you just add, make it more pixels, include bigger pictures, but you need more computational power, more time not to calculate these things. But you see, this is a little brain which is able to memorize and retrieve the information, associate what this brain sees with something that it's in its memory in a not trivial way. And the nice thing is that mathematically we control everything. We know everything about this brain. Okay? So this is it for today. Hopefully it was not too boring. So, and good luck for the rest of the week and starting the upcoming academic year. So I'll see you around.